Well, that's it I guess. In just this one series, I've probably answered to like my top 3 most popular requested videos. So yeah, what better way to wrap things up than to actually summarize everything and then be done with the series. And that is exactly what's gonna happen today. You're watching episode 9 of Sorting Algorithms++, the Wrapup. Hello and welcome back to the final episode of Sorting Algorithms++. Today's video will come to you in 2 parts. First, we're gonna actually summarize all the content we've gone through in the series. So yeah, just my usual quick summary of every single episode with emphasis on how they link to each other. Then we move on to part 2, where we actually take a look at why the hell there are so many sorting algorithms in the first place. Hopefully by the end of this series, I'll be able to paint a complete picture for you. Hopefully it will strengthen your understanding of sorting algorithms and why we need them in general. So enough of that, let's jump right into part 1. We started off this series in episode 1 by actually revisiting the Big O notation. We refreshed our memory regarding what makes an algorithm fast, what makes an algorithm slow, and how we actually express this in terms of a mathematical construct. Then we moved on to take a look at trees. In particular, the binary search tree. The magic that makes a binary search tree even work in the first place is of course the binary search tree property, which actually dictates an ordering for the items inside the tree. In particular, smaller at the left, larger at the right. In episode 3, we took a look at in-order traversal, which takes advantage of this particular property to extract things in a sorted order. However, at the end of the episode, I shattered your hopes and dreams by showing you how you could break the binary search tree. By inserting a sorted list into a binary search tree, you create what is called a degenerate tree, which essentially is a linked list. We also learned right there that the bottleneck for tree sort is in fact the insertion part, not the actual traversal, which is why it is all the more important to actually have a balanced tree, so insertion doesn't take forever. To address this concern, we move on to episode 4, where we took a look at AVL trees, a type of tree that actually balances itself, and as a result, this prevents situations where insertions take a very long time. To very quickly summarize the AVL tree logic, we have to take into account the height of all the branches within the tree, and our objective is we don't want 2 neighboring branches in any part of the tree to have a height discrepancy of 2 or more. Whenever there is such a discrepancy, we'll have to perform rotations to actually fix things and bring things to a balanced level. Of course, we also took a look at great detail regarding the actual rotations, and we established that the way you do rotations, you don't actually break the binary search tree property. By having a tree that balances itself during every single insertion, you'll never get an unbalanced tree that takes a very long time to insert items into. And as such, we decided that for a balanced tree sort gives you a time of O and log n. Having satisfied ourselves with that, we moved on to heaps. We first noted the similarities of heaps with a binary search tree. The only difference is the ordering is now from bottom to top or top to bottom, instead of left to right. In particular, the reason for the 2 different types of orderings is because there are 2 different types of heaps, a min heap and a max heap. The only difference between these 2 types of heaps is the statement of the heap property, and as a result of that, the smallest item is at the top of a heap for a min heap, and the largest item is at the top for a max heap. We then learned that the method to actually sort a list using a heap is to repeatedly extract the topmost item. We then moved on to take a look at how important the complete tree property in a heap is. We can actually use this property to stick a heap into an array. Once we do that, that opens a door to some other cool things we can do. For example, we can build a heap very quickly, seeing as that now it's all a flat array. Sorting can also happen in place. All the movements and exchanges that happen during heap sort can all happen within the input array. After we are done with heap sort, we moved on to radix sort. We took a look at how it is different in the sense that no comparisons were actually made between items in the list. We then took a look at its miraculous time complexity and realized it's not really as miraculous as it seems. However, at the same time, we recognized the ingenuity behind the actual implementation of radix sort. And that leads us here, to our final concluding episode for this entire series. There might be one question in your mind, and that is, why are there so many different sorting algorithms? Well, this brings us to part 2. So, why are there so many sorting algorithms? In particular, why are there so many O and log n sorting algorithms? I mean, they're all equally fast, right? According to the big O notation. Why is it that we need to have so many different ones? I don't think I'll be able to fully answer this question today, but I'll do my best. I'll try to cover as many points as possible. Now, what we've been doing all this time is to actually look at a sorting algorithm and then try to analyze it in terms of its time complexity. However, note that the time complexity we get at the end of the day is the worst case time complexity. That is, when we give a sorting algorithm the most unfavorable data. For example, if you cast your mind back to sorting algorithms Redux, quicksort actually normally runs in O and log n time. However, if you give it a sorted list, it's unable to create partitions and as a result slows down to O n squared. We call quicksort a worst case O n squared algorithm, but in fact, in many situations, quicksort doesn't fare quite as badly as you think it does. So first things first, when we actually look at an algorithm from a general, practical kind of perspective, the worst case time complexity isn't always the most accurate measurement. When choosing a sorting algorithm for use in your program or whatever application you're going for, you must also take into account the nature of the incoming data. Of course, this will require some kind of research into what applications your program is going to be used for, but different applications call for different sorting algorithms. And to illustrate this, I'm going to give you a few examples while at the same time defining a couple of new terms. Now, you might have heard the words in place and stable associated with certain sorting algorithms. In fact, I used the word in place a couple of times. So let's start off with in place. It's a term that we've already looked at with association to heap sort. So here's the deal. Let's say you are writing a program for an embedded circuit. In situations like that, you don't have a lot of memory. As a result, you are not likely to use a sorting algorithm that actually requires a lot of memory. In fact, if memory is the bottleneck, you want to use an in-place sorting algorithm. The reason for that is an in-place sorting algorithm does not incur additional memory use. What this means is you can reliably predict that the amount of memory required for the operation is exactly the amount of memory required for the input data to come in. So if my input data occupies 100 bytes, I know that everything my sorting algorithm does happens within this same 100 bytes. At no other point of time will it create additional things in the memory, and as such, you don't have to worry about running out. Now, a stable sorting algorithm is one that preserves the order of things with the same value. Now, it's true that within this entire series, all the sorting algorithms we've looked at, we've actually tried to trace using a list of all unique numbers, but in reality, sometimes you still get values that, well, are the same. And as a result, your sorting algorithms must still be able to handle those. Take for example the following list, which is currently jumbled up in no particular order. If I were to sort it just by the speed of the algorithms, notice how the individual algorithm names still remain all jumbled up, even though they are now correctly grouped by their speed. If we were to return to the original list, we could actually sort the algorithms by name first. Then we could sort them by speed. And notice how, in doing so, the algorithms are sorted by name and speed. This is exactly the premise behind a stable sorting algorithm. If your application requires you to have a bunch of data that can be sorted again and again using different parameters, you might want to use a stable sorting algorithm, so that the newer pass of sorting doesn't actually destroy the results of the previous pass. Now, let's take a look at another example. Let's say you want to be able to sort strings of text instead of just numbers. Now, most of the algorithms we've covered can actually do this. However, sometimes there might be performance differences between sorting plain numbers and actual text. Like I mentioned at the end of Radix sort, using the same concept for sorting strings is possible, but it will incur a whole lot more memory. So this is something worth considering as well. At the end of the day, there is no one-size-fits-all algorithm that works for everything, and as a result, we have a whole lot of different n-log n algorithms for us to choose from. Now, from what I could gather, one of the more popular O n-log n algorithms used in many places is actually quicksort. You remember that sorting algorithm profiler I showed you in the first episode that I wrote? As you can see, quicksort is actually pretty darn quick. So in fact, it seems that for general situations, quicksort is a good solution. And there you have it. That pretty much wraps things up for all the sorting content I have for you. I hope that this actually gives you a very clear overall picture of basically all sorting algorithms and the concept behind sorting algorithms in general. So yeah, I don't think I have anything else to add. Let us go ahead and wrap up this video. As usual, if you have any comments, queries or suggestions, feel free to leave a comment in the comment section below. I'll be very happy to hear whatever feedback and whatever is not clear. Please do let me know. I'll do my best to help you. Don't forget to check out the official Twitter account for this channel at twitter.com/0612tv. As always, I appreciate every like, favorite and subscription you give me. But until next time, you're watching 0612TV.